So formulation of the drug is an appropriate dosage form is very critical aspect which a medicinal chemist has to look on, right? So the biodisposition of these orally active drugs in the living system are going to alter the administration and are going to affect the absorption, distribution, metabolism, and excretion. The solubility is expressed in terms of its affinity or repulsion, and we will term these following things wherein we all have studied this: hydrophilic, lipophilic, what it means. So hydrophilic is water loving, lipophobic is lipid hating, and lipophilic is lipid loving, and hydrophobic is water hating. So we will see how these are going to affect. So we had already studied how the solubility is being expressed, and this particular table tells us about the relative amount of solvents which dissolve in one part of solute. So when we call a substance is very soluble, the relative amount of solute to dissolve one part of solute is less than 1. When it is freely soluble, it is 1 to 10. When it is soluble, it is 10 to 30. When it is sparingly soluble, it is 30 to 100. When it is slightly soluble, it is 100 to 1000. When very slightly, it is 1000 to 10,000. And when we call the molecule as practically insoluble, then it is more than 10,000. So following are the parameters which affect the solubility. One, nature. Second, temperature. And third is the pressure. So nature of solute and solvent. So here we need to understand and remember covalent bond and the ionic bonds, what we have studied. So polar solvents are liquids made up of polar molecules, whereas non-polar solvent are liquids which are made up of non-polar molecules. So nature of solute and solvent: when two substances are similar, they can dissolve in each other. So polar solutes dissolve in polar solvents, and non-polar solutes tend to dissolve in non-polar solvents. So we call as like dissolves like. So two liquids dissolve in each other because their molecules are alike in polarity, right? Now, nature of solute and solvent: ionic compounds are made up of charged ions similar to polar compounds, and ionic compounds are more soluble in a polar solvent than in a non-polar solvent. So this particular slide tells us about the nature of solute and solvent in which it is going to dissolve, and drug molecules exhibit in different forms, amorphous as well as in crystalline, and then the solubility is being affected. The next parameter what we are going to see is temperature. So temperature affects the solubility. As temperature increases, kinetic energy of solute gas increases and the gas can escape. Solubility of solids in liquids: so it is totally opposite of the one what we have seen in gaseous phase. Solubility of solid increases as the temperature increases. So temperature affects the solubility as the solution is formed. When the temperature drops while you mix the solute and solvent, raising the temperature will increase the solubility. If the temperature stays neutral, the temperature will have minimal or insignificant effect in either of the way. If the temperature is increased when the solute and solvents are mixed, raising the temperature will increase the solubility. Pressure: so when pressure is increased over the solvent, the solubility of the gas is increased because pressure increases gas molecules. Pressure, as we increase the pressure, the molecules strike and the surface on the surface to enter into the solution. So it is governed by Henry's law. So solubility of gas is directly proportional to the partial pressure of the gas above the liquid. Then to move further, we will see how hydrophilicity and lipophilicity is to be equilibrated and how it is going to govern the ability of the drug to elicit its action. So hydrophilicity of a molecule is important parameter for drug in body fluids to dissociate, and hence we have seen ideal properties. Rate determining step is to be known. In case of lipophilicity, lipids are important for permeation of drug substances into the membrane. Then coming further, hydrophilicity is important for distribution, whereas lipophilicity is important for absorption. Hydrophilicity is accessible to receptors and is governed totally by the accessibility to the receptors, whereas lipophilicity is important parameter to be considered to reduce the side effects. Solute-solvent interactions: hydrogen bonding, ionic mobility, dipole-dipole interaction is optimal, and van der Waals forces are determined by studying hydrophobicity, right? So hydrophilicity is used to improve the formation of salts, whereas lipophilicity is improved by esterification reactions. Strong acids, bases dissolve completely in aqueous solution, whereas weak acids and bases are dissolved in non-aqueous solution. So the second parameter, what we are going to study is partition coefficient. So what partition coefficient tells us? We will see that here and how it is going to affect the distribution of the molecules into the membranes. Okay. So we will quickly shift towards the partition coefficient. So we will define partition coefficient as ratio of concentration of drug in aqueous phase upon concentration of drug in the liquid phase. So higher the partition coefficient, higher is the biological action. To cross blood-brain barrier, value of P should be low. So log P is determined by universal system N-octanol phosphate buffer, which is used to determine biological action of which is an additive property, right? So we can give example of here of salicylic acid. So if we want to increase the hydrophilicity of salicylic acid, what we can do is we can add a group of alkene or an aromatic ring. Like I will make amino salicylic acid. And when I'm going to add amino salicylic acid or an aromatic ring, we are going to increase the lipophilicity of the molecule, right? Now, when we are going to increase the lipophilicity of the molecule, this partition coefficient is going to affect the equilibrium constants of drug, and then we are going to get the molecules in two forms. One is ionized and the second is in the unionized form into two phases, right? Now, what factors affect partition coefficients? So partition coefficients are affected by pH, co-solvents, surfactants, and complexation. So partition coefficients are difficult to measure in living system. They are usually determined in vitro in 1-octanol as a lipid phase and phosphate buffer of a pH 7.4 as aqueous phase. And why we use 1-octanol as an universal system? So it has polar and non-polar regions, easy to measure, often correlates with many biological properties, and it can predict the properties using computational mode, right? So partition coefficient P is dimensionless and its logarithm log P is widely used as the measure of lipophilicity. Log P is measured by following method. So one method is shake flask method and the second is by using chromatographic techniques, mostly HPLC, right? Now how important partition coefficient is? So we will see by following points. It is generally used in combination with pKa to predict the distribution of drug in biological system. The factors such as absorption, excretion, and penetration of CNS may be related to log P of the drug. Drug should be designed with lowest possible value and log P to reduce toxicity, non-specific binding, and bioavailability. So this is the revision what we have done about the partition coefficient. It is a measure of drug lipophilicity and indication of its ability to cross the blood-brain barrier. And the formula for unionizable drug, P is equal to concentration of drug in octanol by concentration of drug in water. And for ionizable drug, it is concentration of drug in octanol by concentration of drug in water, right? So methods we have also seen. Applications of partition coefficient, it is the measure of lipophilic characteristics of molecule. It is used to recover antibiotics from fermentation broth. It is used for extraction of dosage from biological fluids, absorption of drugs from dosage form, and study of distribution of flavoring oil between oil and water in emulsion. Now, partition coefficient influences permeation of drug across biological membrane. Following administration, the drug must travel through a variety of membranes to gain access to the target areas. So drugs with extremely high partition coefficient readily penetrate the membranes, while drugs with excessive aqueous solubility cannot penetrate the membrane. So here are the values which are being given and with examples. So ethanol has 0.03, which is hydrophilic, morphine 0.04, aspirin 1.19, a lipophilic, lidocaine 2.26, phenobarbital 5.59, which is intermediate acting, and thiopental, it is 100, very lipid soluble and ultra short duration. This particular table tells us about the comparison between intestinal absorption and the partitioning effect of the ionized forms of the drug with percent absorption. This is again the example of particular category wherein local anesthetics are being explained with pK and the percent ionized at pH 7.4 with the partition coefficient. The next property is about hydrogen bonds. So hydrogen bond is a specific uh, kind of bond which is special to study the dipole-dipole interaction between the hydrogen atom in a polar bond such as NH, OH or FH and electronegative atoms of oxygen, nitrogen, fluorine. So these dipole results from unequal sharing of electrons between atoms within a covalent bond. These are weak bonds and are denoted as dotted lines. The compounds that are capable of forming hydrogen bond is only soluble in water. So when we study hydrogen bonding, we study it into two types, intermolecular and intramolecular. Intermolecular occurs between two or more than two molecules of the same or different compound. Due to this, increase the boiling point of the compound and increase the molecular weight of compound. Hence, more energy is required to dissociate the molecule for vaporization. When we talk about intramolecular, so hydrogen bonding occurs within two atoms of the same molecule. This type of bonding is known as chelation and frequently occurs in organic compounds. Sometimes hydrogen bond develops 6 or 5 member ring due to decrease in the boiling point. So these are the examples of salicylic acid, para and meta hydroxybenzoic acids which are affected. So how hydrogen bonding is going to have effect? So all physical properties are affected by hydrogen bonding, namely boiling melting point, water solubility, strength of acid, spectroscopic properties, on surface tension, viscosity, biological product and drug receptor interaction. Next is chelation, or we also call it as complexation. So chelation and complexation can be explained by complex molecules, or what we call complex of drug molecules, which cannot cross the natural membrane barriers and they render the drug biologically ineffective. So rate of absorption is proportional to the concentration of a free molecule, that is diffusion of the drug. Due to reversibility of complexation, equilibrium between free drug and drug complex occurs. So drug plus complexing agent, a reversible kind of reaction, it gives a drug complex. Complexation reduces rate of absorption of drug but not affects the availability of the drug. Now, complex formation is used in medicine, basically in the antidotes for metal poisoning, wherein dimercaprol and chelating agent penicillamine, which is a chelate of 1:2 ratio, which is used. Next example is 3-hydroxyquinolone and its analog, which act as antibacterial antifungal agent by complexing with iron or copper. Undesirable side effects are caused by drugs, which chelates with metals. A side effect of hydralazine, an antihypertensive agent, is formation of anemia, and this is due to chelation of the drug with iron. Phenobarbital forms a non-absorbable complex with polyethylene glycol 4000. Calcium with EDTA forms complex which increases the permeability of the drug. Next parameter is ionization of drug. So most of the drugs are either weak acids or weak bases and exist in either form, and we call them either form, either ionized or unionized. Ionization is protonation or deprotonation, which results in charged molecules. Ionization of drug depends on its pK and pH. Rate of drug absorption is directly proportional to the concentration of the drug at absorbable form, but not the concentration of the drug at the absorption site. Hence, ionization form imparts good water solubility to the drug, which is required for binding of drug and interacting with the receptor. Unionized form helps the drug to cross the cell membrane. An example, barbituric acid, when we take it, is inactive because of its strong acidic nature, while 5,5-disubstituted barbituric acid has an CNS depressant action because it is a weak acid. So acidic and basic properties are important in both the phases. When I say both the phases, one is the dosage form and second is the pharmacological form, which dosage form is the pharmaceutical phase and pharmacological phase is the disposition, structure at target, etc. So when we are going to see the particular properties, we need to also understand the nature of the drug, and the nature of the drug, when I say it is a characteristic, whether it is an acid or whether it is a base. Now, recognition of acidic or basic functional group is also a very important parameter, wherein I have mentioned here a few examples of carboxylic acid, phenol, sulfonamides, imides, and beta-carbonyl groups, which are common acidic functional groups which are used in most of the drug molecules. Common basic functional groups which are available. So we have aliphatic, primary, secondary, tertiary amines. We have heterocyclic amines and aromatic amines with most of the drug molecules. And this particular parameter is governed by HH equation. So for acids, pH minus pK is equal to log of ionized by unionized. And for base, it is pH minus pK is log of unionized molecule by ionized molecule. And therefore, the percent ionization is calculated.